Hey guys, in this video we're going to talk about Chapter 12, Section 1, Functions of Two Variables. Alright, so in algebra, trigonometry, Calc 1, and Calc 2, we talked about functions of one variable. Typically we had a function called f of x, or g of x, h of x. We also called it y, and that function depended on only one variable. Usually x, sometimes we use t, and any other variable really. So the output depends on only a single input. This is a function of one variable. So let's take a look at an example that you've probably seen before. You start with $50 in your savings account. You deposit $20 into the account every month. And so the output f of x tells us the amount of money in your savings account after the input x months. So how can we write an equation that represents this situation? Well, this is a linear equation, right? Because what a linear equation means is that after a set amount of time, you're increasing by a set amount or you're decreasing by a set amount. So we know that this is linear because every single month, after every 1 unit of time, an extra $20 is coming in. Okay, so that's what tells us it's linear. A set amount of 20 is coming in each month. So we can write an equation that represents this in the following way. We can say, well, f of x, or y, is going to be 20x plus 50. All right, 20 is the set amount, this is the slope, and 50 is our initial value, which is our y-intercept b. So this is a function in one variable. The output only depends on x, only depends on how many months has passed. Okay, so let's go ahead and look at this in the form of a table. We've done this a bunch of times in algebra, but I just want to refresh your brains so that we can take this up a notch to the next dimension. All right, and that sounds kind of intense, the next dimension, but it's really not too bad. So we have x, and then we have y, or f of x. And so remember that we can choose our x values because x is the independent variable here. So I'm going to just pick 0, 1, 2. And my output, well, the first output is going to be 20 times 0 plus 50, and that's going to give us 50. The second one is 20 times 1 plus 50, that's going to give us 70. And the second one is 20 times 2 plus 50, which gives us 90. So this is a table representation of a function, one variable. We came up with some inputs, and we got some corresponding outputs based on the rule, which is the equation. All right, cool. So we got tables there. We can also graph these things if we want to. It's really easy to graph functions in one variable. Remember this? We had an x and a y axis. I'm sure all of you guys remember this. But the way that we plotted linear functions is typically we'll start at the y-intercept, which is 50, and then we'll rise, overrun 20, and get the next point, and so forth and so forth. So we have a graph-like picture for this. Now I want you to think, if we extended this to have two input variables and one output variable, how would the graph look different? Could we use a two-dimensional plane to represent such a graph? And the answer is no. We actually have to extend our picture for a graph. We have to add in a new axis, and we're going to get to that in just a few slides. But for now, I want to really focus on the equation and table aspect of what we're learning next, which is functions in two variables. Okay, so this is exciting. This time, we have two inputs, and just for the sake of consistency, I'm going to call the two inputs x and y, and we're going to get an output of z. So this is analogous with our one variable example where we had our output of y and our input of x. So this time we have two inputs, x and y, and our output is going to be z. So the output Z depends on two variables, X and Y. All right? And maybe, and let's do some examples here, okay? So we have a situation. Robin pays $5 per pound for cat food. Maybe I should change this to 4, better grammar. And $10 per pound for dog food. What is the total cost of the pet food that she buys? Well, that depends on two things. It depends on how many pounds of cat food she buys, and it depends on how many pounds of dog food she buys. Right? Depends on two things. That's the key distinction here. So how can we write an equation? Well, we can say Z is our output. So our output is our total cost. Let's write that down here. Well, actually, maybe let's name the variables first. Let's say that Z is the total cost. This is the output. Let's say that X is the pounds of cat food that she buys. And let's say that Y is the pounds of dog food that she buys. So we can come up with an equation here. We can say the output is equal to what? How much is the total cost going to be? Well, it's going to be 5 times the number of pounds of cat food, right? Because it's $5 a pound, plus $10 per pound per how many pounds of dog food that we buy. This is going to be the total cost. So right here is our equation in two variables. We have a variable Z, our total cost, depends on two variables. The first variable is the number of pounds of cat food that she buys, and the second variable is the number of pounds of dog food that she buys. All right, so let's play around with this a little bit. Now our table, we need to extend the table a little bit because this time we have two inputs and we want to do this in a sort of organized way. So this is what I'm going to do. This is how we're going to tackle this. I'm going to make row up here. I'm going to do this, and I'm going to say, well, this is going to be 0, 1, 2, 3. Up here, I'm going to have 0, 1, 2, 3. And these are going to represent both of my inputs. So I'm going to say that this guy is going to represent X, and this guy is going to represent Y. So I have two sort of inputs here. And the rest of the table that I'm going to fill out is going to be my corresponding outputs. So let me just draw some rows so we can get our feet wet here. What's going on? Okay, so what do you think goes in this first box right here? What do you think goes in that first box right there? Well, this corresponds to having an input of 0, right? That's the X row that we're in. And another input of 0. That's the Y column that we're in, okay? So I'm in the X column 0. Sorry. I'm having issues talking today. I'm in the X row 0, and I'm in the Y column 0. So this box that I'm filling in happens when X is 0 and Y is 0 in this equation. So just like we did before in one variable, we're just subbing in 0 for X and 0 for Y. And solving, or evaluating rather. So 5 times 0 is 0 plus 0. So our output is 0, that's what goes here. And that makes sense, right? If you don't buy any pounds of cat food, if you don't buy any pounds of dog food, the cost is going to be $0, right? Makes sense. Awesome. Let's try another one. So let's look at this one right here. Okay, so this is the X row is 0, so X is 0, and the Y column is 1. Y is 1. So when X is 0 and Y is 1, what do we get? Well, we get Z is equal to 5 times 0 plus 10 times 1, and that's going to give us an output of 10. So what does that mean? Well, that means if I don't buy any cat food, and if I buy 1 pound of dog food, it's going to cost $10. That makes sense, right? It says dog food is $10 a pound. If I buy 1 pound of dog food, 0 pounds of cat food, my total cost is $10. That's our output. All right, so you guys can check my math here. This is how you do it, though. This is how we can fill out the table. So we get 20, 30. Again, I'm just looking for the corresponding x and y's and filling them into my equation. So like this guy right here, this happens when the x row is 1 and the y column is 0. So x is 1, y is 0. And so in my equation, I get z is equal to 5 times 1 plus 10 times 0, and that's going to give us 5 as our output. So I'm spending $5 for 1 pound of cat food and 0 pounds of dog food. That's the real world interpretation here. Okay, and so you guys can check my math here, but I'm going to just fill in this table with our values that we get. You guys should verify that these are the ones that you're getting to, just to get some practice using these kinds of tables. All right, cool. So what's neat about this, we just bumped it up a dimension, right? We are now in 3 dimensions. We have 3 variables, x, y, and z. 2 inputs, x and y, 1 output, z. And what is awesome about this is that we can treat these coordinates just like we did when we had when we were in 1 variable, when we had 2 dimensions, right? We listed ordered pairs. X is 1, y is 0 would be 1, 0. Well, now that we're in 3 dimensions, we can list our ordered pairs as ordered triples. We can have 3 numbers in each pair corresponding x, y, and z. So that the ordered pairs go x, y, z, like that. And so what we can do is I can just list a few of them, a few from this table. Well, okay, everything in the boxes, like all of these, are our outputs. All of those are our outputs. And so we can write the corresponding x and y here. So like, you know, firstly, we know that 0, 0, 0 is a point. This is x, y, z, and we saw that when x is 0, when y is 0, z is 0. You guys see the picture here? Let's do another one. Let's do this, 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 right? So when x is 2, y is 1, z is 20. When x is 2, y is 1, z is 20. That's another ordered pair, x, y, z. Let's do one more. How about this one right here? This one. So I'm in the x row that I'm in is 1, right? The x row that I'm in is 1. The y column that I'm in is 3. So when x is 1, y is 3, and z is right here, 35. All right. So how do we plot these in the coordinate plane? Well, we're gonna answer that in just a few moments, but for now, let's look at this. Which of the following points lie on the graph? We don't know what the graph looks like, but we can still do algebra. Which of the following points lie on the graph of z equals 5x plus 10y? So that is the function that we came up with for the dog food cost, and we're trying to see which of these points make the equation true. So, which points make the equation true? let me go back to 2 dimensions, okay? So we can have an analogy. If I gave you y equals 3x plus 1, and I said, is the point 0, 1 on the graph? If I said, is that point 0, 1 on the graph, what would you do? You would plug in your corresponding x and y values into this function and see if you get a true equation. So you would say, oops, sorry guys, you would say 1 is equal to 3 times 0 plus 1, is that a true equation? On the right, I evaluate to get 1, and that is true, so yes, it is on the graph. If you get a false equation, such as 2 equals 10 or whatever, it's not on the graph, okay? Hope you guys get the picture there. So let's bump this up to our 3rd dimension, and we're just doing the same thing. We're seeing when we plug the points into this equation, are we getting a true statement? If yes, then it lies on the graph. If no, then it doesn't. So for the first one, x, y, and z are all 0. We know this lies on the graph, but let's prove it algebraically. When x is 0, y is 0, and z is 0, we get 0 equals 5 times 0 plus 10 times 0. And the right side simplifies to 0, so yes, this is on the graph. The next one, 1, 2, 25. Well, x is 1, y is 2, and z is 25. Plugging this into our equation, we get 25 is equal to 5 times 1 plus 10 times 2. And simplifying the right side, I get 25 equals 25. That's true. That's on the graph as well. What about 6, 3, 24? Okay, so x is 6, y is 3, z is 24. Plugging this into the equation, we get 24 equals 5 times 6 plus 10 times 3, okay? Simplifying the right side, I get 30 plus 30 is 60. That is false, so that is not on our graph there. And let's do the last one, 8, 1, and 50. So x is 8, y is 1, z is 50. Plugging this into our equation, we get 50 is equal to 5 times 8 plus 10 times 1. So we get 50 is equal to, let's see, yeah, so that's going to be 40 plus 10 is indeed 50, so this one is on our graph. So the only one that isn't is C. All right, let's do some more practice with this. I encourage you guys to pause the video and try this one on your own. Which of the points lie on the graph of this equation? Well, again, we're just trying to see which of these points give us true equations. Let's check point A, x, y, z. If I plug in, and this is the equation that we're referencing right here, I'm plugging in 4 for x, 8 for y, and 6 for z. Okay, so 4 minus 8 plus 6 is going to give us 4, negative 2 equals 2. Is that true? 2 equals 2? Yes, it is. So this one is on the graph. Next one, x is 0, y is 1, z is 3. So we have 0 minus 1 plus 3 equals 2. That checks out as well. So that one is on the graph. Let's do the next one, negative 1, negative 4, and negative 5. I have negative 1 minus a negative 4 plus a negative 5. Does that equal 2? Well, these double negatives become a positive, and I'm left with negative 1 plus 4. Positive and negative becomes a negative. And I'm left with negative 1 and a negative 1. This is a negative 2, not a positive 2. So this is not on our graph. And the last one, we have x, y, z. So negative 4 minus a negative 6 plus 1, is that equal to 2? Negative 4 plus 6 plus 1 equals 2. And we get 3 equals 2. So that's not true. All right, so the only two that lie on the graph are A and B. The next thing I want to touch on is whether or not a function in 2 variables or an equation in 2 variables represents a function. So let's go back to one variable. How did we determine whether or not an equation was a function in one variable? Well, we did it two ways. The first way is that we just looked at the graphs, right? And we employed the vertical line test. So if a vertical line can pass through the graph and only touch one point for every, points on the, every point on the graph, if it passed the vertical line test, then it was a function. So like this guy right here passes the vertical line test because you can draw a vertical line anywhere on the graph and it only passes through one point. Whereas this guy does not pass the vertical line test because he hits 2 points right here. So that was one way. Another way of looking at it is, by definition, y is a function of x if there is exactly one output for each input. So an input cannot have multiple outputs. Let's write that up here. An input cannot have multiple outputs. So we're going to extend this idea into 3 dimensions. Now we're not going to use the vertical line test. We haven't talked about graphs quite yet. What we're going to do is just think about this algebraically. So let me show you what I mean. Let's extend our definition to 2 variables. Z is a function of x and y. So z is a function of x and y if there's exactly one z, exactly one output for each input x and y. Okay, so it's the same idea in two variables. We can't have 2 different inputs going to, or we can't have the same inputs going to different outputs. Okay, we can't have that happen. So let's take a look at some examples of functions versus non-functions in two variables. So our first function here is z equals 3x minus 5y plus 1. This is a function because, we choose the inputs for x and y, and we're only going to get one output for z. There's no way that we can get multiple outputs for two inputs. However, we do have a problem whenever we see a square. Sometimes we do. And the reason is that if we solve for z in this case, we have to square root both sides of the equation. So when I solve for z, I square root both sides and I get z by itself is equal to plus or minus the square root of 5y minus 6x. And the plus or minus is the problem because, for example, if say x is 0 and y is 1, then we have z is equal to plus or minus the square root of 5 times 1 minus 6 times 0. And under the radical, that just becomes 5. So z is equal to plus or minus root 5. So we have 2 outputs. We have positive square root of 5 and negative square root of 5 for the inputs 0 and 1. So that can't happen. That's why that's not a function. So let's do some practice with this. If we're given this equation right here, determine if z is a function of x and y. So we have to isolate z and see whether or not we have square roots involved, basically. So let's go ahead and do that. We start with 15x minus 6y plus 8z equals 24. Let's go ahead and get z by itself by first adding 6y to both sides and then subtracting 15x from both sides. So I get 8z is equal to 24 plus 6y minus 15x. And now I'm just going to divide everybody by 8 and simplify. So I get z is equal to 24 over 8 is 3. 6 over 8 can be simplified to 3/4. And 15 over 8 can't be simplified. So is this a function? Well, yeah, because we don't have any plus or minus here. We don't have two different outputs corresponding to the same input. So yes, this is a function. Let's take a look at another example. So here we're given the equation x squared plus y squared plus z squared equals 9. Is z a function of x and y? If so, give the formula. So again, we're just going to start by isolating z. And to do that, I'll first subtract x squared. And then I'll go ahead and subtract y squared. So I get z squared is equal to 9 minus x squared minus y squared. And now we have to square root both sides. And when we square root both sides, we need to make sure that we're tacking on a plus or minus when you physically take the square root of both sides. And because of this plus or minus, because of this is a problem. We have two different outputs for the same pair of inputs. So no, this isn't a function. That's our answer here. So the next thing that we need to talk about is how to actually graph ordered pairs in 3 dimensions. Right? In the previous examples, we could come up with ordered pairs. We could use equations to verify if points were on a graph, but now we actually need to graph these things. So in 2 dimensions, when we just had x and y variables, we had an x-axis, which was horizontal, and a y-axis, which was vertical. Now we need to introduce a z-axis, and let me explain how we do it. We take the x and y axis, and we imagine taking it, picking it up, and placing it under your feet, okay? So x and y axis, just imagine standing on it, okay? You're standing on that, and above you is the positive z-axis, and below you is the negative z-axis. So you're on the ground here. Your x-axis is this red guy, and I want you to imagine this, the positive x direction, as coming out of your screen, coming out of your computer screen, okay? You're standing flat on this thing, and you look up, and here's your positive z-axis. You look down, and there's your negative z-axis. You look to the right, and down, and that's your positive y-axis, and then to the left is your negative, your positive y-axis, and to the left is your negative y-axis. So the red one is x, coming out of the page is your positive x, receding into the distance is your negative x. This guy right here is your positive y, this is your negative y, this is your positive z, this is your negative z. So let's practice plotting some points in 3 dimensions. Now there's a point here that's already plotted, and that's C, and we're going to do that one last, just to show you how we get there. But the first one I want to look at is point A, which is x is equal to 1, y is equal to 2, and z is equal to 0. So we always start at the origin, right? We did that in 2 dimensions, and x is 1, so I'm going to go ahead and just mark off 1 in black. X is 1 right there. Then I go to the y component. Y is 2, so I move along the y-axis 2 units. And I want to see where these guys intersect when I draw parallel lines through them. The first parallel line I draw is through the x point that's parallel to the y-axis. Okay? And the second line I draw is parallel to the x-axis through the second point. And where these guys meet is right here. Now, we don't have a z component, so we're not moving up or down. We're on the flat ground. This is our point A right here. All right, so that's point A. Now let's go ahead and look at point B. So point B, we have an x component of 3, a y component of 4, and this time we do have a z component of 5. So I'm first going to mark off x is 3, that's right here in black. Y is 4, that's right here. I'm going to go ahead and draw my parallel lines, and you can kind of see that they're already drawn for you on this picture, but if you don't have a grid like this, you can kind of just eyeball it on your own. So there's x is 3, y is 4, drawing that parallel line through there, and their intersection is right here. So this is the thing right here. I'm going to project upwards, okay, because there's a z component of 5. I'm going to project it upwards 5. Now, what students commonly, the big mistake is they're going to just say, oh, well, z is 5 right here, so I'm just going to make the point right here. And that's not accurate. Because we're in 3 dimensions, it's not going to look exactly like this. Let me show you how we can do it, though, to make it look as accurate as possible. What I'm going to do is I'm going to first draw a line through the point, projecting it, and I'm going to just draw it going straight up, so it's parallel to the z-axis right here. Okay. Now what I'm going to do is I'm going to start at z equals 5 and do my traveling along the x-axis and the y-axis so that I can meet this yellow line and see what the intersection is. Okay, so I'm traveling along the x-axis first. I want to go 3 in the x direction from z equals 5. So if I take my x equals 3 and kind of just make this parallel line to the z-axis, and then I go parallel 3 units in the direction of x, I'm going to end right here. So I went 3 units in the direction of x. Now I need to go 4 units in the direction of y, which again is going to it's going to hit this yellow line right here, right? Because this occurs when y is equal to 4. And I know it's kind of trippy to look at it like this, but this is the way that you do it by hand. So I'm going to travel over 4 units in the direction of y, and I know it's 4 units because we already projected this thing y equals 4 upwards. And so this is my point right here. This is B. So, and you can see that it's not exactly at a height of 5, but it is because we're in 3 dimensions. Imagine this is the front of a cube, all right? This is our point B. We can see that it's a little bit below the 5 here. So that's our answer there. And let's go ahead and do C. Try to do this one on your own for practice, and then I'm going to show you a little shortcut, or a little maybe cheat code, I guess. Okay. All right, so for C, again, we're employing the same idea here. And C is already plotted, but I just want to show you, like, prove how we get there. So this time x is a -2, so I'll mark it. I'm going to mark it in black right here. X is -2, going away out of the receding into the distance. X is -2. Y is going to be 4, so I'll mark that here. And then I'm going to first get my point on the xy plane so that I can project it upwards 5 units. Okay, so how do I get that point? Well, I make the parallel line here, parallel to y, parallel to x, and I see where their intersection is, and it's right here. So this is the point that I'm projecting upwards, and you guys can already see it projected upwards here. But how do I get there? How do I make this picture as accurate as possible? Well, I can start with my z component. Z is equal to 5. And z equals 5. Well, let me actually draw my line just like I did with the other one, and we don't know where it's going to stop, but there it is. So the first thing is from z equals 5, I'm going to travel along the x-axis -2 units. So I'll draw this guy parallel to the z-axis, and I'm going to travel along this guy parallel to the x-axis 2 units, and so I stop here. So I just traveled from my starting point, which was here, to my ending point here. I traveled along in the x direction 2 units. Now I'm going to go ahead and travel along the y direction 4 units, which we know is going to stop here. Okay, so that's our point right here, C. Okay, so that's how we get the most accurate picture. Now I'm going to show you something awesome, because when we actually start doing the calculus, you're not going to want to draw all of these pictures. I mean, you can, but one really, really nice tool, it's kind of like Desmos, it's called GeoGebra. So if you Google GeoGebra 3D calculator, this tool is very, very helpful. It's going to be extremely helpful in Calculus 3. And this is what it looks like. You can download the app as well. Just type in the App Store GeoGebra 3D calculator, and it's going to look like this. And you can spin it around, move it like this. If you want the X and Y labels, what we can do, let me see if I remember how to do this. We go to this little hamburger at the top left and click it. And then I'm going to go to settings, and then I'm going to go to, let's see, labeling maybe? No, not labeling. Let's go to algebra. No, let's go to graphics. Okay, graphics. You see where it says labels at the bottom? We're going to click that, and then we're going to just hit this little button at the top to show my X, Y, and Z labels. I like it that way. I mean, you don't have to do that, but I like it. Then I'm going to click that little hamburger at the top again. I'm going to go back to settings, and I don't want the plane to be showing that gray flat plane. So I'm going to go over to algebra. No, I'm going to go to graphics, and I'm going to click the little off button for show plane so that I just have that plane thing right there. Okay, now what I'm going to do is, just like Desmos, I can input stuff in this little bar, and I'm going to see what my points look like here. So the first point that we graphed was 1, 2, 0. So I'm going to just do ordered pair 1, 2, 0. And, oh, I didn't see. Okay, so there it is, and it labels it for you. It's labeling it A, and you can see that this was the point that we graphed. It's on the ground. It doesn't have any Z component. But yeah, you can verify your picture with this little tool. And we're going to use this a lot in this class when we start talking about surfaces and so forth. So anyway, that's how we do that. Let's go ahead and do some more practice with this so that we can wrap our head around it. It says, describe the position of the point 1, 2, 3. All right. So this is, again, 1 is X, 2 is Y, and 3 is Z. So now it's just telling us to describe it. We can describe it first and then actually plot it. So describe it. We're going to start at the origin. 0, 0, 0. And then we're going to go 1 in the X direction. Then we're going to go 2 in the Y direction. And finally, we're going to go 3 units up in the Z direction. So that's just the description. Now let's actually plot it. So 1, 2, 3. So again, I'm starting with my X's and Y's first. I'm going to plot X equals 1 first. That's right here. And then y equals 2 is right here. I'm going to draw my parallel lines and see where they intersect. And that's going to be this point right here. This is the point that I'm projecting up 3 units. So I'm just going to draw a straight line through it, up, 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 parallel to the z-axis. And then what I'm going to do is I'm going to start at the z-axis at z is equal to 3. I'm going to travel 1 unit in the direction of the x-axis. So if I start at 1 and just kind of draw my line parallel there, and then draw my line parallel to the x-axis, I end up right here. And then I'm going to go 2 in the direction of the y-axis, which we already found where that stops. It's gonna stop at this point right here. So this right here, let me do it in a different color. How about purple? This is the point 1, 2, 3. And let me just erase everything so you guys can see where it is. Okay. All right, describe the position of the point 0, 0, negative 1. All right, so let's first do the description first. So firstly, we don't have an x and a y component. We only have a z component. And so, so what this is really saying is we're not moving in the x or y direction. Going down 1 unit in the z direction. Okay, so that's pretty easy. So we start at the origin right here, and we're just going down 1 in the z direction. So this is my second point right here. This is the point 0, 0, negative 1. All right, and again, you can use GeoGebra to verify this, so please do if you're having trouble seeing this. Okay, let's do another example. You start at the origin, go along the y-axis at a distance of 2 units in the positive direction, and then you move vertically upward a distance of 1 unit. What is your final position? Okay, so let's go ahead and think about this. Let me just draw a little sketch here. So there's my z, and my x is maybe like that, and then my y. Okay, so this is y, x was red, and z was blue. Okay, so we go 2 units in the y direction, so 2 units in the y direction, positive y direction, and then we move up a distance of 1 unit, so we don't move in the x direction at all. So we only move up 1 unit, and so this is going to be our position right here. And what point is that at? Well, we're not moving in the x direction, so that tells us x is 0. We moved 2 in the y direction, so y is 2. And we moved up 1 in the z direction, so z is 1. So this is our final position here. This is our point. All right, so I've been throwing out this word plane, but now I actually want to talk about what a plane is. So it says, let's just look at an example. Which of the equations z equals 0, z equals 3, and z equals negative 1 look like? Basically, let's compare this to the two-dimensional idea. Let me just bring this back here, and then we can move on to the three-dimensional case. If I gave you the equation y equals 1. This is a horizontal line through y equals 1. So this is something that looks like this. This is y equals 1. And what this means is the following. This means x can be anything, but y must be 1. Do you see that in the picture? X can be literally whatever we want, but the output, the height, has to be 1. That's what that means. In a similar way, if we had x equals 3, what this means is y can be anything, but x must be 3. That's what that means, guys. So how I draw that is, so this was y equals 1. I draw this as a vertical line. This is x equals 3. Right? Y can literally be anything. Y can be whatever it wants to be, but the x value has to be 3. That's what that means. So let me go ahead and extend that notion to 3 dimensions. What do you think z equals 0 means? Well, what that means is x and y can be anything. Maybe I'll do this in blue since the picture's blue. Sorry guys, let's go ahead and do that. So this means x and y can be anything, but z must be 0. And the picture is a plane. Imagine it as a flat sheet of paper. This is our picture of the equation y equals 0. Notice that this covers all of x and y. X and y can be literally anything, but z has to be 0. It has to be a flat sheet. It can't have any height associated with it. Do you guys see the picture? So let's go ahead and move on to the next one, z equals 3. That's going to be the one in green. So this means x and y can be anything, but z must be 3. That's going to give us this flat sheet of paper up here, this green sheet of paper. If you were to plug this equation into GeoGebra, this is what you would see. This is going to be the equation z equals 3. X and y can be anything. This paper extends out infinitely long in the x and y direction. However, it has a height of 3 and it stays at a height of 3. It doesn't change in height, okay? Same thing with z equals -1. So z equals -1 is this little pink plane down here. So it says, hey, we have a flat sheet of paper. That means x can be anything, y can be anything, but the height is fixed at -1. Okay, so this is z equals -1. And I encourage you guys to plug these equations into Desmos and mess around with them here. Okay, so let's go ahead and move forward here and talk about the specific planes that we're interested in. The first one is the xy plane. We just looked at this. That was when z is equal to 0. So this means the xy plane covers the entire x and y axis and leaves out the z axis. So this is z equals 0. X and y can be anything, but z is equal to 0. Okay, covers the whole x and y axis. The YZ plane contains the y and z coordinate axis, and this occurs when x is equal to 0. So we can see this flat sheet of paper extending infinitely in the y and z direction, and x is fixed at 0. Okay, so this is the graph x is equal to 0, also known as the YZ plane. The XZ plane contains the x and z coordinate axis, and this occurs when y is equal to 0. So here is y equals 0, and we can see that our sheet right here extends infinitely in the x and z direction. Okay, so the sheet of paper doesn't stop. It just keeps going in the x and z direction, but it's fixed at y equals 0. It doesn't move in the y direction. All right, which of the points listed below, A, B, C, or D, lies closest to the XZ plane? Okay, so let's take a look at this in GeoGebra. All right, and hopefully you guys are gonna get the concept by seeing it visually like this. So we have our points listed here, and we also have the XZ plane, which I listed on the very top row, y equals 0. That's the XZ plane. And so we're tasked with seeing which of these points is closest to the plane. And guys, the only distance we're looking at is the y distance. We're trying to see which of these points lie closest to the plane in the y direction. That's the only thing that matters. The x and the z coordinates do not matter. It doesn't matter, if we have a point way above B. All that matters is the y direction. So which has the the smallest distance in the y direction? Well, if we look at our y coordinates, for A we have -1, for B we have 3, for C we have 2, and for D we have -4. So the closest one is A because the distance in the y direction is the smallest, right? In other words, the absolute value of y is the smallest for A. So since the absolute value of y for A is the smallest, absolute value of -1 is 1. That's the distance, right? So since the absolute value of y is the smallest, A is closest to the XZ plane. This only, closest to the XZ plane only depends on the distance of y. All right, so that was our first question. The second question was, which points lie on the y-axis? Points lie on the y-axis if both x and z are 0, right? Because think about 2 dimensions. I always go back to the 2-dimensional case when we had x and y. If something was on the x-axis, y was going to equal 0, right? Well, in this case, something's on the y-axis if both x and z are 0. And so this only occurs at point D. And again, we could put all of these into GeoGebra, and we can see that D does indeed lie on the y-axis. It's the only one that lies on that green axis. Okay. Moving on. So we have 3 points, and we're being asked some questions. Which point is closest to the YZ plane? So the YZ plane is when x is 0, right? And so just like before, when we were looking at the XZ plane, that depended on y. So on y distance, this time we're going to be looking at x distance. So what we're trying to see is which x distance is the smallest. Okay, and so we're going to look at our x values and compare all of the absolute values of these guys, and we can see that the absolute value of 22 is 22, which is the smallest, and so our answer here is going to be A. Sorry, not A, C. C is 22. Okay, out of 22, 61 and negative 50, the absolute value of 22 is the smallest. Which of the points lie on the xz plane? So this is another phrase for y equals 0. So which of these points has 0 in the y coordinate? Well, the only one that has that is C, right? So our answer here is going to be C equals 22, 0, 0. So that is the only one that has a y coordinate of 0. Okay. Last one. Which of the points is farthest away from the xy plane? So this is just code name for z equals 0. So we're looking at the z distance this time. So the absolute value of z. Greatest. Where's the absolute value of z the greatest? Well, if we look at our z coordinates, we have 5, 31, and 0. And the greatest one is going to be 31. So this is going to be B. Our answer is B. That's the furthest from z equals 0. Again, this only depends on z. And if you're having trouble visualizing this, I do encourage you guys to plug these planes into GeoGebra. So plug each of the planes in, y equals 0, z equals 0, and x equals 0, and then look at your points and try to make that, that distance connection. Okay. You're at the point -3, -4, -7, standing upright and facing the YZ plane. Let's go ahead and put this information in GeoGebra. So the YZ plane, remember, that is just code for the equation x equals 0. And we want to also plot the point -3, -4, -7, and it should look like this. Okay, so I plotted both the point and x equals 0 to see that plane, making sure that I tilt the axes such that the x-axis, the positive x-axis, is going out of the page just like we normally see it, and the y-axis, if we kind of tilt this, we can see that the orientation is going to the right, positive, to the left, negative, and z is positive up, negative down. So this is our standard orientation for our XYZ plane. And we can see our point right here. And so the directions say we walk 1 unit forward, turn left, and then walk for another 1 unit. What is your final position? So the key idea here is that we're not moving up and down, so we're not going to change z. So that's our first clue here. We're moving forward and left, so we're not moving up or down, so we're not changing z. And so we have something, something, and our z is still going to be at -7. We're still at the same height. So if we go back to our picture here, what we can see with A is if we walk forward, we're moving in the x direction, and you guys can tilt this to see it however you want. But when we're walking forward, imagine walking towards the YZ plane. We are getting less negative and more positive. So if we walk 1 step forward, then we're going to add an additional +1 in the x direction. So we're moving 1 forward in the x direction, which means that instead of -3, -3 plus 1 is going to give us an x position of -2. So that's going to change to -2. And then it says that we're going to turn left once we walk forward. I got to be careful not to click that point. And we're going to move 1 to the left. So notice that the left is indicated with the y-axis. If we go 1 to the left, we're getting more positive in the y direction. Okay, so that we're just adding 1 to y. So instead of -4, since we're going left 1 unit, we're going to be at -3. So our final position is at -2, -3, -7. So let's plot that. Okay. All right, so that is position B. And so then we're asked some questions about this. The first question we are asked is, well, we already took care of the final position. Now it says, from the point of view of an observer looking at the coordinate system, are you in front of or behind the YZ plane? So are we in front of the YZ plane or behind it? In front or behind? Well, we're behind it, right? Because we're in the standard orientation. We have positive X coming out of the page. We have positive Y going to the right, and the negative going to the left. So we are behind. We can see that point B is behind the YZ plane. So let's answer that here. All right. So then it says, is this point B to the left or to the right of the XZ plane? So remember, the XZ plane is just when Y equals 0. So I can change this just to see what my plane looks like. Y equals 0, and then I get my picture here. And then I'm just going to orient this in the standard way. So I have X coming out of the page, positive Y to the right, and it says, is it to the left or to the right of the XZ plane? So it's to the left of it, right? It's going to be to the left of it. So that is going to be our answer here. We can see that those points lie to the left of the XZ plane. And the orientation is important. Remember, the positive X is coming out of the page. The positive Y is going to the right. Positive Z is going up. So this is to the left of our plane there. So this is going to be to the left of XZ plane. And finally, it says, is this thing above or below the XY plane? So remember, guys, the XY plane just occurs when Z equals 0. Excuse me. So I can plot Z equals 0 to see what's going on here. Instead of Y equals 0, I'm just going to change that to Z equals 0. All right, and we can see, again, we're just going to make sure our orientation stays consistent, and we can see that these points, both of them, A and B, are below the XY plane. All right, the next thing we're going to talk about is distance between 2 points in 3 dimensions. So again, we're talking about all of this because we're going to do calculus on 3-dimensional objects. And this is the most real world that we're going to get because we live in a 3-dimensional space, right? And so a really useful notion is distance in 3 dimensions. So what I want to do is I want to sketch out a little proof of the distance formula in 3 dimensions using the Pythagorean theorem. Now, it's pretty easy to prove the Pythagorean theorem in 2 dimensions. I'm not going to do that here just for time's sake, but if you guys are curious, you should look up a video of it. So what I want to do is I want to set up the proof in the following way. I want to set up 2 arbitrary points in space. The first point is ABC. The second point is XYZ, and I want to come up with a method to find the distance between those 2 points. Now, in this picture here, that distance is represented by this length PG. Okay, so that's what we're trying to find. Now, take a look at ABC. What I want you to think of is I want you to think of this as sitting in the middle of a 3-dimensional coordinate system. So let me draw this. And actually, I shouldn't have done that in red. Maybe I'll do it in a different color. But maybe we'll just keep blue here. No, we use blue for Z. Let's do yellow. That's a good color. That's what we're trying to find, that yellow distance. So remember, with our 3D coordinate system, I'm just going to sketch it over here so you guys can hopefully see where I'm going with this. My blue is Z, my red is X, and my green is Y. I'm just not extending out in the negative direction. So this is Y, this is Z, and this is X. And that's what I want you to think of right here. You see in the back of this cube right here, we have our Z, we have something parallel to X, and then we have our Y right here. Now, ABC does not have to be the origin. It doesn't have to be 0, 0, 0. It's just an arbitrary point in space. That's how we want to think about it. But we want to think of the blue, red, and green as being parallel to the Z, X, and Y axis, respectively. So, how did we get the labels here? Well, the first label here is X minus A, this right here. And the reason is because that's the distance between the X value here and the A value here, right? It's the difference between the two. This guy is sticking out front, this guy is way back there. So that's the difference in X and A with respect to the X-axis. In a similar way, if we look at B and we take a look at this segment right here, this segment is Y minus B because it's the difference between Y, where Y is, and where B is. Okay? Yeah, so that's Y minus B, and in a similar way, we have Z minus C is going to be this guy right here. This is the difference in the Z values between Z and C, right? That's going to be the difference in height, basically. And we can see that because, you know, C is flat on the ground, right? This is where C is flat on the ground, but up here, Z is way up here. So the difference between the two is this segment right here, and hopefully that makes some sense to you guys. So now that I've labeled everything, the rest of the proof is pretty easy, okay? So let me go ahead and just erase some of this. So what we want to do is we want to look at two separate triangles and apply Pythagorean theorem. Now, the idea here, like the whole thing we're looking for is this, right? That is going to be PG, which is the distance between ABC and XYZ. That's what that means. So look at the bottom of the cube. All right, so imagine looking at the very bottom of this cube. We have a triangle right here. A right triangle specifically. And we know some things about this right triangle. Let me actually draw it like this, kind of standing up, so you guys can see it a little bit better. We have the bottom is Y minus B. That's the length of the bottom of that triangle. This part right here is equal to this part, which is X minus A. So I'm going to label that as such. And we don't know what the diagonal is. Okay, we don't know what the diagonal is. So let's go ahead and solve for the diagonal, and then we're going to use this triangle to find PG. All right, so let's go ahead and solve for the diagonal, which is PF. Maybe I'll actually write that here. And this is what we're looking for. Got to find PF first so that we can find PG. Okay, so let's go ahead and do the Pythagorean theorem. We have A squared plus B squared is equal to C squared, hypotenuse squared. All right, let's go ahead and I'm not going to expand this out at the moment. What I want to do is just solve for PF, so I'm going to square root both sides. And so I get PF is equal to the square root of x minus a squared plus y minus b squared. So that's PF. That is this section right here. Well, actually, maybe I'll do this in a different color. How about we do it in green? This guy right here is the square root of x minus a squared. Oh, I don't like green. How about we do it in purple? It's just not showing up the same, you know? I'm going to just label it over here so we have room. All right, so we have this is equal to x minus a squared plus y minus b squared. That's what that section is equal to. Now, we know what that section is, right? And what you want to imagine, I'm going to draw this, I'm going to project it in 2 dimensions, just like we did with the orange triangle. What you want to imagine is your triangle is like this. Okay, so we have our height, we have our base, and we have our diagonal, and this is what we're trying to find right here. This is PG. Okay, so you want to kind of imagine your triangle in space right here. Okay, so there's our triangle projected into 2 dimensions. We just found the base, that purple part. That was x minus a squared plus y minus b squared, square root of that. Now, what's the blue component? Well, the blue component is the height of this cube, which we just mentioned was z minus c, right? That's the height of the cube. So this is going to be z minus c. So now we can do Pythagorean theorem. So we say, well, one leg squared plus another leg squared, which is z minus c, is equal to pg squared. That's what we're looking for. That's the big thing. Pg is the distance. All right, so let's clean up the left a little bit. And the only thing I'm going to clean up is I'm going to cancel the square with the square root here. And so I get the following. I get x minus a squared plus y minus b squared plus z minus c squared is equal to pg squared. And finally, to get pg by itself, remember that was the whole goal. That's the distance between 2 points. I'm going to go ahead and take the square root of both sides. So I have pg isolated. Pg is equal to the square root of x minus a squared plus y minus b squared plus z minus c squared. So this is our distance formula in 3 dimensions. This, well, actually, maybe I should point to this. This gives us the distance between the points ABC and XYZ. All right, pretty cool, right? This is the distance formula in 3 dimensions. So let's go ahead and use this. We want to find the dimension, or we want to find the distance between the points 1, 2, 1 and negative 3, 1, 2. So I'm just going to start by writing my distance formula. Instead of PG, I'm writing distance is equal to the square root of x minus a squared plus y minus b squared plus z minus c squared. Okay. All right, so our first point we can call, you know, x, y, z, or if you wanted to, you could say it's a, b, c, it doesn't matter. So this one we could say, well, it's x, y, z, and then the second point is a, b, c, and then we'll just plug in these numbers into our formula to get the distance. Pretty straightforward there. So we got the square root of x is 1 minus negative 3 squared plus y minus b squared plus z minus c squared. Alright, so this is going to give us 1 plus 3 is 4 squared is 16 plus 1. Negative 1 squared is 1 again. So this is going to be the square root of 18. And that's our answer. That's the distance between the two. Alright, which of the points listed is closest to this point right here? Well, for this, we're just comparing distances, and we're seeing which has the smallest distance, basically. So the distance between P1 and P, we're just plugging this into the distance formula. You know, I have negative 4 minus 1. So I'm just taking this component minus this component, squared, plus, next one is 6. 6 minus 2 squared plus 3 minus 9 squared. Let's see what this gives us in the calculator. That's going to be 25 plus 16 plus 36. I'm getting root 77, so this is the distance between P1 and P. And we just do the same kind of thing for the second one. So distance between P2 and P. We got 4 minus 1 squared plus negative 4 minus 2 squared plus 2 minus 9 squared. Again, just taking the coordinates and subtracting their respective coordinates from P and squaring them. So this is going to give us 9 plus 36 plus 49. That's going to give us a square root of 94. So distance between P2 and P. Alright, P3 is negative 8, 6, and 2. Negative 6. Oh wait, sorry, that was negative 8, not negative 6. Negative 8 minus 1 squared. 6 minus 2. And then finally 2 minus 9. So I get the square root of 146. All right, let's do the last one, P4 and P. All right, so P4 is negative 3, negative 1, 3. Alright, so we have negative 8 minus negative 3 squared plus 6 minus negative 1 squared plus 2 minus 3 squared. Okay, so this is going to give us negative 8 plus 3 is negative 5 squared is 25. 6... this is going to be 7 squared is 49, and then this is going to be 1. So we have 50, and 25 is going to make the square root of 75. So this is the distance between P4 and P. All right, so let's see which one is smallest. Square root 75, square root 146. The last one is going to be the smallest. Square root of 75 is smaller than any of those other numbers. The cube is located such that its top 4 corners have the following coordinates. Give the coordinates of the center of the cube. Okay, so I've already plotted these coordinates on GeoGebra, and so these 4 points are going to make up the top of our cube, the corners. And so the idea here is to start at a point, travel halfway along the x, travel halfway along the y, and travel halfway along the z-axis to get to the center. Okay, so what we need to do first is we need to find out how long the sides on our cube, the side lengths of our cube, basically. So to figure that out, we need to use the distance formula, and you can use any of the sides, but I'm gonna just start by using start by finding the distance between A and B. So the distance between A and B by our formula is going to be the square root. So A is this first ordered pair and B is the second one. So by our formula we have -2 minus a -2 squared plus -3 minus 0 squared plus 5 minus 5 squared. Alright, so let's go ahead and simplify under the square root sign. -2 plus 2 is going to give us 0 squared, which is 0. -3 squared is 9, and then 5 minus 5 squared is 0 again. So we just have the square root of 9, which is equal to 3. So the distance between A and B is 3 units, right? That's going to be the total length between A and B. Now, because we want to get to the center, we want to travel halfway along the y-axis, right? This is parallel to the y-axis. You see this yellow point here in the y-axis. These guys are parallel. So we want to travel halfway along the y. We also want to travel halfway along the x, and you can see that it's going to be parallel to the x. If you see these two guys, and then we want to travel down halfway in the z direction to get to the center of the cube. Okay, so let's go ahead and employ that mathematically, and we can start at point A. It doesn't matter which point you start at, but we'll start at point A at the point -2, -3, 5. Now, the first thing that I want to do is I want to travel in the y direction, right? These are parallel. And I want to travel halfway. So half of 3 is 1.5. So I want to travel 1.5 in the y direction first. And I'm going to the right. So I'm going to be adding 1.5. So plus 1.5 in y direction. So I'm just going to make this like step 1. I get -2. Then I'm going to do -3 plus 1.5 for the y, and then leave everything else. And that's going to land me at -2. Sorry, my brain isn't working that fast today, so I'm just cheating using the calculator a little bit. Okay, so we're at this point when we travel 1.5 in the y direction. That's this distance right here. Then what we want to do is we want to travel 1.5 in the x direction, right, to get halfway there, because I'm trying to get to the center of the cube here. So Now what I want to do is I want to do plus, because I'm moving this way, which is going positive in the x direction. So I want to go ahead and add 1.5 in the x direction. And that's going to give us, well, -2 plus 1.5 is going to give us -0.5. So I have -0.5, -1.5, and 5. Okay, and finally, I want to travel down, right? Because this is the top of the cube. So I want to travel down 1.5 units to get to the center. And so that corresponds to subtraction, since I'm going down along the z-axis. Right, okay, so this was step 2. And then finally, step 3, I want to do minus 1.5 in z direction. So everything's going to be the same except 5 minus 1.5 is going to give us 3.5. And this is our answer. This is the coordinate of our center. So that's where the center of this cube lies. You know, if we were to extend this downward like so, we would see that the center is going to be exactly at that ordered pair. All right, so let's talk about spheres, okay? So in 2 dimensions, in 2D, we have circles. And circles have a center and a radius. And the same thing applies to spheres, which is basically like a basketball shape. So a circle has a center and a radius, and so typically we call the radius r, and the center we can call maybe a comma b. And so the equation of the circle okay. Oh, sorry, this isn't y. This should be r squared. All right, so the equation of the circle r squared equals x minus a squared plus y minus b squared. And basically what a circle is, it's the set of all points equidistant from the center, equidistant by r. So we're going to apply this concept to a sphere in 3 dimensions. Now a sphere is all points r away from the center. Okay, maybe r is 5. So a sphere of radius 5 would consist of every single point 5 away from wherever it's centered. Okay, so let's go ahead and take a look at this. And notice that, you know, all we're doing is we're using the Pythagorean theorem in 3 dimensions here. Because when you try to find the distance between a point on the sphere and the center of the sphere, so let's say we're trying to find the distance between x, y, z from the center ABC, and you know, we know what that distance is. By definition, it's r. And so by the Pythagorean theorem, we have this equation for the sphere. And if you take the square root of both sides, your r becomes your distance, right? So this is the equation of a sphere centered at A, B, C. It looks just like this. Okay, and that is just an application of the Pythagorean theorem. That's how we got that. All right, so let's go ahead and take a look at this example. With the z-axis vertical, a sphere has center 6, 3, 7 and lowest point 6, 3, 0. The question is, what is the highest point on the sphere? All right, so we know our equation of a sphere is r squared equals x minus a squared plus y minus b squared plus y minus c squared. Okay, and the center, we're told, is at 6, 3, 7. So that's our A, B, and C. And we're told that the lowest point on the sphere, which is going to be right here, this point is going to be 6, 3, 0. And what we're trying to figure out is what is the highest point on the sphere? What is the highest point on the sphere? Well, to do this, I mean, this is not too much of a problem. All we have to do is count, right? We're trying to figure out what the radius of the sphere is, because this distance right here is going to be the same as this distance up here, and we can easily figure out, what our highest point is from that. So if you notice, we're just going down from the center to get to the lowest point, so we're only changing in z. And so we're going from z equals 7 to z equals 0. Well, what does that tell us about the radius? It tells us that the radius is 7, right? That's a difference of 7. So that means that r is equal to 7. That's this distance right here. And if that distance is 7, this distance is also 7. But instead of, since I'm at z equals 7 and I'm going up, I'm going to add 7 to that to get my highest point of 6, 3, 14. 7 plus 7. So this is going to be my highest point. Okay, so here we have a classic sphere problem. We have two spheres in 3D space. Sphere A has a radius of 5 units, and it's centered at 2, 3, 1. Sphere B has a radius of 4 units, and is centered at 8, 1, 6. And we want to determine if these spheres are in collision, meaning they intersect or touch each other. And so the idea here, the big idea here is this. If the length from the centers of the sphere is smaller than or equal to the sum of the radii, we have a collision. And so the way that I've drawn it, it looks like the spheres just touch each other, right? Because this distance from center to center is going to be the same as the sum of radius 1 right here and radius 2. Right? That's going to be the same exact distance. So, and I haven't drawn them perfectly because if I move them around, they overlap a little bit. But you want to imagine that the sum of the radii is the same as the distance from the center. So that's one case. Or what if I drew it a little bit differently? Maybe I put the sphere way over here, maybe over here. And so we can see now that if I extend the radius here, extend the radius here, so this is R1, first radius, this is R2, second radius, and then the distance between the centers is going to be represented by this orange. And it's pretty clear that the distance represented by the orange is much larger than the distance of R1 plus R2, or the sum of R1 plus R2, right? And so they're not colliding. We can see this pictorially, right? But on the other hand, if I move this over here, let's move it. Well, actually, that's not going to work. But the idea here is that if they're overlapping, the distance from the center is going to be smaller than the sum of the radii, okay? So let's go ahead and use this little blip right here to answer our question. All right, so let's write what we know about sphere A. It has a radius of 5 units. So this is sphere A. This is a radius of 5 units. And the center is going to be at 2, 3, 1. Sphere B has a radius of 4 units. Maybe I'll do him in purple. So sphere B has a radius of 4 units and is centered at 8, 1, 6. Again, I haven't drawn these spheres, how they would really look in space based on the coordinate system I laid out, but you guys, can get the idea here. So here's our two spheres. We have the centers, we have the radius, and we want to know is the length from the centers smaller or equal to the sum of the radii? Well, the sum of the radii, we have the sum of radii, radiuses, I don't know which one you like better. It's going to be 5 plus 4, which is equal to 9. Now we need to know what the distance, the length from center to center is. That's what we want to see next. So we want to do the distance from 231 to 816. This is just the length, right? And so we use the distance formula. We're going to do the square root of 2 minus 8 squared plus 3 minus 1 squared plus 1 minus 6 squared. Simplifying this out, 2 minus 8 is going to give us negative 6 squared is 36, plus 2 squared is plus 4, plus negative 5 squared is plus 25. All right, so putting this in our calculator, we have 36 plus 4 plus 25, and that's going to give us square root of 65. Now, if I put the square root of 65 in the calculator, I'm going to get 8.06. And so we can see that the distance from the center is smaller than the sum of the radii, so we have a collision. Right? 9 was the sum of the radii, and 8.06 is the distance from the centers.